All right, guys. I know that it's been some time since we were last together, so I don't want to just kind of start off where we were. I'd like to kind of regenerate this theorem. It's actually our textbook calls it the corollary. Spend a little bit of time on it, and then it expands ultimately into another corollary, which is really the same idea, just look at the different segments. And then spend some time on that. If I do this over the next day or so, we're getting towards the end of the chapter. So at the earliest, maybe Thursday, chapter test, latest Friday. Missing the last 2 days of class actually kind of puts us behind schedule, so we're going to try to have to make those days up somehow. Some kind of spitballing some things there. We're going back to what we kind of finished with on Wednesday. Okay, we said if we're working in a right triangle, so this has to be inside right triangles, and you have to have this segment DB drawn inside the triangle, and that's your altitude. Okay, so you have this interior altitude being drawn from the right angle to the hypotenuse. When it intersects the hypotenuse, it breaks it into two segments, right? Okay. So we got that green segment and that purple segment. What this corollary says is that distance of dB, that altitude, it is a geometric mean between the green distance AB and the purple distance BC. Okay? And we did a problem like that, and I think the bell rang, but what I want you, and all the problems that we do, guys, are going to be of this fashion, but they're not going to have the same letters A, B, C, D, and all that kind of stuff. So what I think is maybe a little bit more important is to actually take the physical words that are in the corollary and set them inside our proportion. So I'm going to put altitude here. I'm going to put the word interior in parentheses because there's three altitudes. This is the only one that's on the inside. And it goes here as well. Okay. Then what goes in this numerator is parts of the hypotenuse, and what goes here is the other parts of the hypotenuse. Okay? The only thing, so if we're going to use that, the only thing we have to realize that we all agreeing on is that when I use the word hypotenuse, because of the way that these three triangles are created, the green one has a hypotenuse, the blue one has a hypotenuse, and the overall one has a hypotenuse, right? And they are different segments. When we're saying the hypotenuse in this corollary, we're talking about the overall hypotenuse, AC. Okay? And that's going to be the case in all these problems that we do. When we say, what is the hypotenuse? We're talking about the hypotenuse of the original right triangle. Okay? If we can remember that, I think that's going to go a long way in helping us work through some of these problems that we're going to be encountering as we work with this situation. Okay? Now, like I said, that only works if this is constructive. If that segment is not there, or you don't know if it's a right angle, or you don't know if the overall triangle is a right triangle, you cannot do this. So this works in one situation. You got a right triangle overall, and you're drawing the altitude from the right angle to the hypotenuse. Okay? Now, the idea is that this segment is an altitude. But if you remember, when we talked about right triangles in chapter 4, and talked about altitudes in chapter 4, that leg is also an altitude. This leg here is also an altitude. The altitude of a right triangle is going to be one on the inside, which here is dB, but the legs are also altitudes. So what happens here is that we can actually take these values out and replace with the legs. Okay, and that's going to change the extremes as well. So I'm going to come down here and I'll give you this to write down. It says when the altitude is drawn to the hypotenuse of a right triangle, so it starts just like the last corollary. Okay, so you've got to have this overall right triangle. You have to draw DB to the hypotenuse. When that happens, this now starts talking about each leg. It says each leg is the geometric mean between the hypotenuse, again, the overall hypotenuse, and now the segment of the hypotenuse that is adjacent to that leg. So I'll give you a minute to write that down, draw that picture, and then we'll fill in these proportions and then kind of generalize those proportions like we did in the last one. Kind of line by line. It says each leg. So let's just talk about this leg AD. Okay? It says each leg is the geometric mean. So AD is going to have to go there and there. That, by definition, is what we mean by a geometric mean. Okay? Now it says between the hypotenuse. Well, what was the hypotenuse of the overall shape here? What was the largest hypotenuse up there? AC. Okay? Remember, we're talking about the height. If we remove the colors and all that kind of stuff in the triangles, there's one giant right triangle. Okay? And that's what we started with. Its hypotenuse is AC. Okay? So it says the geometric mean between AC now, and now the part of that hypotenuse. So every time I draw this segment down, this interior altitude, it's going to create this point B. And when it creates point B, obviously that is my altitude, but it's going to take my altitude and break it into two separate segments, right? Which one of those, the purple one or the green one, is touching AD? A to B, right? Okay. So that's what they're referring to here. We'll put AB right there. That is the leg, or not the leg, that is the part of the hypotenuse that is touching the leg that you use in the geometric mean. Okay? My hopes are you see that the green segment does not touch that leg at all, right? Okay, they're complete. If we were to kind of highlight or eliminate everything else, because some people struggle seeing this, let's actually do this real quick. Let's go. And just color over so there's our leg AD. Okay, now here's my hypotenuse. Would you agree that that portion of the hypotenuse B to C is not touching AD? That makes sense to everybody? But if we do this, that portion of the hypotenuse A to B is touching AD. Does that make sense? So I think maybe redrawing some things or resketching, highlighting, that kind of thing can help visualize that. Okay? So that's one relationship that we see by looking at that first leg. The other leg can come into play, though. The other leg would be D to C, right? So our legs are the ones that make the right angle. So there's my right angle. So CD is a leg as well. So that's a geometric mean. Now it says it's a geometric mean between the hypotenuse. So AC is my hypotenuse, right? AC is my hypotenuse. And now what part of that green segment is touching the leg we chose that was CD? Everybody agree that's B to C? Okay. You should see it when you work with your extremes, the way we name them. Okay, AC and AB here, they share point A. That's where they touch, is at point A. Here, these share point C. That's where they touch, point C. Okay. If I didn't write it that way, there would not be kind of that. I mean, when we put it in a picture, we don't see that visual of where they're touching there, where they're adjacent, where the leg is touching that part of the hypotenuse. Okay, so that's great and fine, but I don't necessarily like that because, again, the pictures might not have AC, AD, and AB. So if we get down to stuff like this, we're using, that one uses those letters. This one uses different letters. This one doesn't use letters at all. Okay? So what I want to do here is, like we did up here, when we wrote it as part of a hypotenuse over an altitude equals altitude over the other part of the hypotenuse, we can structure this the same way. Okay? So this, I'm going to write as what went in the geometric mean spot was a leg. So leg there and leg there. I always keep my numerator in this first fraction as the whole hypotenuse. And this would be part of the hypotenuse touching the used leg. So when if I'm in your seat, I'm not saying this is right or wrong, I'm just saying this is what I would do. And I get to a test, I get to a quiz, I get to my homework, I'm going to write this at the top of my page. Okay? I'm going to write that other one we wrote previously at the top of my page. And if I've got those, I should be able to take every one of these pictures that we go through and develop the ratios, the proportions, and the accompanying ratios the correct way. Okay? Now, all of these, so these are corollaries, which means they come from some other theorem, okay, and they flow directly from some other theorem. So let me go back real quick to this picture here. You guys remember working on this problem right here a few days ago? Okay. Basically what happens there, if we were to look at the 9 ratios that we have set up here, and I've colored over them, all that kind of stuff, okay? Those ratios right there, if you look at it right here, AC and AC, is AC a leg? Does that make sense? So this first one, we got a leg and a leg in the geometric mean position. Now AB, is AB the entire hypotenuse of the overall triangle? So that's why that AB went there. Is AD then the part of that hypotenuse that is touching the red leg? So that's why I went there. Okay? So this corollary is telling us no matter what set of right triangles you look at, if you draw that altitude down from the interior, from the right angle to the hypotenuse, you will always undoubtedly create a grouping of ratios in which, when we group 2 of them, there will be legs in that spot, and then the hypotenuse, and then the part of the hypotenuse touching that leg. Here, we see the other leg. Here, we're seeing BC being the geometric mean. Between AB, which is the hypotenuse, and then DB, part of the hypotenuse that's touching that leg. Over here, we're seeing CD being the altitude in the geometric mean spot between the parts AD and DB of the hypotenuse. Okay? So this corollary is allowing us to create those relationships much faster than what we did when we first saw question 14, working solely with similar triangles and writing the similarity statements from those similar triangles. Okay? So let's kind of just jump into some practice problems here. Okay? I'm going to add some things to these problems. So I'm going to make that Z. So there's 3 distances here I want to find, X, Y, and Z. My suggestion to you, and this is something that I think is paramount for a lot of questions in this course, a lot of courses that have like problems that have contextual aspects to them. I mean, they have story problems, they have pictures. They're not so much like Algebra 1 and Algebra 2 where you're just factoring things or solving equations. Here, there's context to what I've got to do. I don't try to dive into this and say, let me find the one equation that deals with X. Let me find the one equation that then deals with Z and then Y. What I do is I holistically look at this picture and try to come up with all the relationships that I know, all the linkings of the parts that are up there that I know, and then I say, okay, once I write those out, are there any that allow me to solve for a variable easily? Okay? So using the idea that we just talked about, let's just look at that segment right there. That's a leg, right? Okay. Well, we just said the leg should be a geometric mean. So Y should go there, and Y should go there. Does that make sense? Now, it's the geometric mean between the hypotenuse. What would be the hypotenuse in this overall triangle? P to R. Remember, so that's my right angle of the overall triangle, so then this is my hypotenuse. So the leg is the geometric mean between the hypotenuse, so 6 is going to go there, right? Okay? Now, what part of that 6 touches the leg that we used? P to S. So 2 is going to go there. So I'm not going to solve that yet, because it's coming up with statements for finding Z and X is going to be a similar process. So when I'm kind of in the mode of doing one thing, I try to do that one thing as many times as I need to. And then I'll go back and I'll solve each of them. So now we know that that was one leg, but aren't there 2 legs for every right triangle? So isn't that a leg as well? So is that a geometric mean? So we put X there and X there. Now it's the geometric mean between the hypotenuse. Do you agree that that's still the hypotenuse? So 6 is going to go there. Now what part of that hypotenuse is touching the blue leg now? 4. And now I can solve for X. Okay. Before I do that, I'm going to set up a relationship for Z. And Z is now that segment there, correct? And that's the altitude that we talked about Wednesday, where that is now the geometric mean. Now, it's a little bit different, okay? Instead of looking at the entire hypotenuse as part of my ratios, it's now just parts of the hypotenuse. So 2 and 4 are going to go here and there. Okay. Last class asked, does it matter where the 6 and 2 go, or the 6 and 4? Can they flip-flop spots? Can the 2 and 4 flip-flop spots? And because I'm going to multiply, it's 6 times 2, same thing as 2 times 6. Yeah, so it doesn't matter. You can interchange the extremes if you want to. But what my hope is, when we do these problems, guys, is that we see those 3 blue segments. Okay? And we're going to target an individual relationship for each of those blue segments. And once we target those, then go back and solve them. That make sense? Okay? We're going to get in a habit. A lot of the questions you see in your homework, a lot of questions I've got here in the presentation, your variables show up in the mean spots quite a bit. They don't have to be variables. You can put numbers there. If you know, maybe they say, and I think we do see one here in a little bit, where instead of it being a Y down there for PQ, they make it 8. So you put 8 in both those spots. Okay? But one thing that happens, and this is the reason I like this, is that when it's variable, when you cross multiply there, don't you get Y squared? And when you cross multiply there, you get 12, right? How do I solve for Y here? square root. So I'm going to say y is equal to square root of 12. Okay. I've been kind of leading this with comments throughout the last couple of weeks that radicals and simplifying radicals eventually will be something that we do and we are asked to do consistently. Okay. The reason I'm going to ask you to do this is because of how much you use them in Algebra 2. Okay. And at that point when you're in Algebra 2, it's just assumed of you that you know how to work with radicals. Okay. So you're going to have to simplify this. They might ask you to write 2 decimal places, 3 decimal places, that kind of thing. If it's decimal places, go ahead and use your calculator. If you want simplified, can we use our calculator? And the answer to that is going to be no. Okay. What we're trying to do is break this down so we divide out the largest perfect square. So what perfect square will divide 12? When I say divide, I mean what will give me a quotient that is a whole number. Does that make sense? I can take 12 and divide it by anything. There's only a finite number of things that will give me a result that is a whole number. Does that make sense? Like 12 divided by 2 will give me a whole number of 6, right? So 12 we say is divisible by 2. 12 is divisible by 3, gives me a whole number of 4, right? Okay? So I'm looking for one of those whole numbers that I get back that is going to be a perfect square. And it's going to be the largest possible perfect square. Okay? Now, in that respect, and understanding that I need to get a whole number back, the only way that I can take 12 and divide it so I get a whole number back is as long as I divide it by something that is less than half of 12. Does that make sense? Take 12, so half of it is 6, right? If I divide 12 by anything bigger than 6, it's going to give me a number between 1 or 0 and 2 back. Does that make sense? Okay. But if I divide it by anything less than 6, it's going to give me back 2 or something greater. Okay. So when checking what are the largest perfect squares, all I need to do is check the perfect squares that are less than half that number. So 6 is half that number. What is the only set of perfect squares that are less than 6? 1 and 4, right? So 4 divide 12 evenly. All right, so it's going to divide it like this. Give me 3 as a result. Okay? But what's the square root of 4? It's 2, right? So we get 2 radical 3. I'm not sure that everybody understands this, so let me write this real quick. If I have radical 16, that is a symbol for what number that you multiply itself by. Okay, now this next part's going to change per what root we're taking. But there's a 2 out here. There's an understood 2 out in front of the radical. So multiply by itself, in that case, that many times, 2 times, to get what we call the radicand, which in this case is the number underneath the radical, which is 16. So what number can I multiply by itself 2 times to get 16? 4, right? So radical 16 is a numerical representation, or let me say it this way, a symbolic representation of the numerical value 4. Okay? Much like this is a symbolic representation of 3.14 whatever, right? Okay? Now all numbers underneath the radical will give me an integer like 4. Okay? So we've got to kind of pay attention to that. Like, so radical 12 will not give me a rational number like 4. Okay? So the next one, I'm going to go x squared is equal to, I'm going to rewrite this as 6 times 4. Okay? Now the reason I'm going to do that is I'm going to take square root. What's square root of 6? Is there a perfect square that divides 6 evenly? Nope. So square root of 6 is already simplified. Okay? But what's the square root of 4? 2. So it makes sense that goes down to 2 radicals 6 right away without. If you really sit down and think about it, when you do simplifying of radicals, there's an aspect of division that's taking place. Okay? Well, to get x squared equals 6 times 4, I'm going to first multiply and then undo it with division. Why even multiply in the first place? So I usually don't. Okay? Now, if you want to, you can. You can say x squared is equal to 24. And now think, okay, well, what's 24 divide by? 6 and 4. So get me back down to saying that's the same thing. Does that make sense? Okay. Some people like to take 24 and do this. 2 and 12. 2 and 6. 6 goes down to 2 and 3. I can group those as a pairs of 2, right? And that grouping of 2 is actually the 4 that I take the square root of to get that 2 out in front. And that grouping of 2 and 3, they don't have partners. And the reason I'm looking for partners is because a number times a number gives me a perfect square, right? So 2 and 3 don't have partners, so they become partners, multiply them together, and they go underneath the radical. Okay, that's probably the first way you were taught how to simplify radicals last year. Okay, z times z, over here would be z squared. I'm going to leave it as 2 times 4. So then z is equal to radical 2 times radical 4, which was square root of 4? It's 2, right? Do you guys know, and I've talked about it, it's up there on the board for the last class, but I want to explain something that I think some people overlook, or maybe you're told last year, but not really understanding why this happens this way. If I have, let's say, the square root of A times B. Okay, so some product. So like I had earlier, maybe radical 24, or maybe I just leave it as 6 times 4 like that. How do I know that I'm allowed to do this? Okay, I want to walk you through that process. The first thing I need you guys to know is that by definition, a square root is actually, and any root is this way, is actually the use of a exponent that is a fraction. Okay? So if I take a square root of 9, what do we expect to get square root of 9? 3, right? Okay? Now, if I take this and write it as square root of 9 to the first, still gives me 3, right? Okay? Now, you remember, I told you there was a number out front here, right? Tells me how many times I'm multiplying a number by itself to get 9. So I'm taking 3 and multiplying it by itself 2 times to get 9. What about if I go square root of 16 to the first? I get 4, right? These are numbers that I expect to get, right? What if I take it and rewrite it as 9 to the fraction of 1 over 2? Does that still give me 3? The 16 to the 1 over 2 still give me 4? Does that make sense to everybody? And that fraction of 1 over 2 is coming from the fact, like I said, there's a 2 out here. You're taking the exponent of the 9, and that becomes your numerator and your fraction. And then this, we call that the index. Okay? Tells me what to take the root of, how many times. That becomes my denominator of my fraction. Okay? So when you want to take the square root of something, it is exactly the same thing as raising that number to the 1/2 power. So when we come back to this here, if I have AB as my product, I can rewrite that as AB to the 1/2. Does that make sense? Okay. You guys remember doing this kind of thing last year? If I have like A squared B to the third and I raise that to the fourth, you guys remember rewriting that as A to the 8th, B to the 12th. And all I did is I took that 4 and multiplied it by that 2, right? And then that 3 by that 4. And the reason for that, think about this. A squared means A times A, right? B cubed means B times B times B, right? So if I do the inside and now look at that as a power of 4 there, doesn't that actually mean that you now have 4 of these things? You have A times A times B times B times B. Come on, paste. There you go. 4 times. Does that make sense? So there's once. There'd be once, twice, 3 times. And now this would be the 4th time, right? And these are all being multiplied together, so the commutative property exists. So how many A's would you have being multiplied together? There's 8 of them, right? So A times 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 A, better written as 8 to the 8. How many B's? 12 of them, right? Does that make sense? So we called that a power to a power. We have a power to a power. Okay, you take that 2, multiply that by that 4, and you get your 8. 3 times that 4 gets you that 12. But the logic of it is that stuff there. So the power here for that A and that B right now are 1. Raising to the power of 1/2. So I get A to the 1/2 times B to the 1/2. Is that okay with everybody? But then we say if we have a 1/2, that's the same thing as taking the square root of A to the 1st and the square root of B to the 1st. Does that make sense then why I can take some product and rewrite it as that? Does that make sense, everybody? So the way we word this, a lot of times they'll say the square root of a product is equal to the product of the square roots. Okay? Square root is the product. It's equal to the product and the multiplication of those 2 square roots. So you're allowed to separate them that way. That is going to be critical for us being able to simplify these radicals. Okay? As we talk about this algebra, and I know that this is a thing that we like to do, okay, what I'm worried about is that when I get to the end of course exam, and I'll double check this later on. So somebody said, well, I got a calculator that does this for me. Okay? Well, if I'm in the end of course exam and I'm using the end of course exam calculator, maybe I don't have access to a handheld, and I'll have to look to see if actually the test might exclude some of your handhelds that you use that do this process for you. My fear is that they ask you to simplify something and you have no idea how to do it. Okay, because you've always relied on the calculator to do it for you. The end of course exam incorporates Desmos, okay, but it restricts some of the operations that Desmos has. Okay, so like Desmos, like if I type in a square root of, I don't know, let's go 72. Maybe Desmos doesn't do it. I thought one of these calculators will actually rewrite that as 6 radical 2. Okay, and it looks like the internet's not going to work for me. But some calculators do it. My fear is that you're going to get a situation where your calculator is taken away from you, okay, for whatever reason, and you get stuck. Okay, you get to Algebra 2, Mr. Malk is going to require this of you. You get to college algebra, I'm going to require it of you. You get to trigonometry, I'm going to require you to be able to work with these radicals. When you go integrated, okay, you're going to be required to do this stuff without a calculator. You go to statistics, you absolutely 100% have to be able to do this without a calculator. Okay, so working with the radicals is a very important aspect of algebra, and that algebra is pervasive in all the other courses. Let's jump down to this example. No, this one. All right. So find X, Y, and Z based off of the information that's up there. And this is one of the problems, guys, and you're going to see a lot of these, that I am afraid that we're going to try to target that right away. Say, okay, what can I write that incorporates X? What can I do here that generates X for me right away? And I think that's a terrible thing to do, okay, because it's not going to be that easy to do. What I want you guys to focus on is that there should be a relationship that exists because of that leg. There should be a relationship that exists because of that green altitude. And there should be a relationship that exists because of that purple leg. Let's create those three relationships and let the variables fall where they fall, let the numbers fall where they fall, and then when we're done, look at the three proportions and see which ones are easier to solve. Okay? So doing this, let's look at that red leg first. So legs are geometric means, right? So I'm going to put Y here, put Y there. When I'm looking at that red one, okay, it's a leg, so it's the geometric mean between the hypotenuse. What are you going to call the hypotenuse of this triangle? What are they referencing as the length of the hypotenuse? X. Okay. That's my entire hypotenuse. That's opposite that right angle. And now what part of that hypotenuse is adjacent to or touching this segment Y? What part of X is touching Y here? 6, right? Does that make sense to everybody? Okay. So your hypotenuse is broken up into two segments. Purple one and the blue one. The blue one's not touching this red segment. Okay, so 6 is the option there. Now, here's where I was saying we might generate equations that are not really solvable right off the get-go. I've got two variables in it, right? Y squared equals 6x. That doesn't make a whole lot of sense to me right now. Okay, maybe after algebra 2, you know that's a parabola, you can maybe do some stuff with that, but right now, I'm going to keep going. I'm going to try something else. Okay, let's look at the other leg since we're in the mode of working with legs. So that is my second leg. So I should go there and there. I should be able to answer the same response if that's the entire hypotenuse, right? So X will go there. Now the next part is where we occasionally run into trouble. Would you guys agree that this distance here is the part of the hypotenuse that is touching the red leg? Do you know how big that is? Say again? Close. Oh, 6. It's going to be X. They're going to be the total thing, X, and then remove 6. That makes sense? Okay. 6 plus X would be something like this if that was 6, and that was X. Then to find the whole hypotenuse would be 6 plus X, right? Still a segment addition postulate allowing me to find that green distance, but we have to use the idea of subtraction to do that. Not the greatest of equations because there's two variables. So I'm going to go look at the third relationship that we're allowed to generate. That right there. That's an altitude. So it's a geometric mean. Now here's where this is different. And everything we've done so far, the geometric mean has been variable, right? It's been a letter. It doesn't have to be. It can be a number that we put there. Okay? So we'll put 8 there. Now, it's the geometric mean between that segment there So 6. And that segment there. That segment, that blue one, we've already found as being x minus 6, right? So I write down everything I know, because you guys know a squared plus b squared equals c squared. There's some stuff in the Pythagorean theorem that would confirm a lot of the work we're going to do here. But the immediate information, those 3 proportions are true. Which one of those is easiest to solve? Third one, right? I get 6x minus 36. I cross multiply equals 64. 6x is equal to 100. X equals 100 over 6, which is 50 over 3. Okay? This is why I kind of focused earlier in the year on leaving things as fractions. If I change that to a decimal, okay, it's going to be a repeating decimal, right? It's never going to end. And at some point, I got to plug it in for the x's in the other parts, and then I get inaccurate values for z and y. Does that make sense? If I leave it as 53rds, we should be able to do our algebra here and figure out what z and y are exactly. Okay? So I'm going to come over here and find y first. I think it'll be easier. I put 53rds there. Across multiply, I get y squared equals 53rds times 6 over 1. Wasn't that 300 over 3? What's 300 over 3? 100, right? Square root of 100? 10. And that's an exact answer. Where if I would have rounded 53rds, I would not get something like 100 or 10. I would have gotten like 9.99 or 9.98 or 9.97, depending on how. Okay. The next one is a little bit more difficult, but the answer turns out to be really nice. When I plug x in, so x was 53rds. So 53rds over z equals z. Now I got to go 53rds minus 6. Well, 53rds minus 6 looks like that with a common denominator, doesn't it? And that ends up being 32 thirds. So you get that. So when I cross multiply, you get z squared, 50 thirds times 32 thirds. Okay, what's 3 times 3? Let's do the denominators. 9. Okay, I'll save you the trouble. That's 1600. So I get z squared is equal to 1600 over 9. Square root, you get that, right? Now, because of the exact same laws of exponents that I showed you that allowed you to take a product apart and rewrite the square root of a product as the product of the square roots, okay? The square root of a quotient is equal to the quotient of square roots. So you can do this. What's the square root of 9? 3. What's the square root of 16? Would you get 16 times 100 is 1600? What's the square root of 16? 4. What's the square root of 100? 10, right? What's 4 times 10? 40. So z ends up being 40 thirds, okay? Which is a number I would not have gotten if I would have used 50 thirds as a decimal, okay? So that's why we do things as fractions. They make the upcoming algebra more convenient when we have to use additional algebra. There's a assignment in Math Excel due tomorrow evening. I anticipate some questions over it, some issues with it. So make sure that you don't wait until tomorrow to look at it. I want you to be able to answer or ask and answer those questions in class tomorrow. before that thing is due tomorrow evening.